exact equation. Now, in exactness, we will have 2x y dx plus 1 plus x squared dy equal to 0. Now, we will now go for what we call the exactness test. Exactness test. First of all, what is the exact equation? This is m function of x, comma y, differential x, plus m is a function of x, comma y, differential y is equal to 0. This is an expression for exact first order differential equation. So if partial m function of x, comma y respect partial y is equal to partial m function of x, comma y respect partial x, it is said to be an exact equation. We must first of all test the exactness condition. Once it is exact, then you can now, that's the criterion to progress and solve it as an exact equation. So that is to say, m is a function of x, comma y is equal to 2xy, because this is the format, this is the relationship. Now, the whole of these are m function of x, comma y. That is the implication. So that is to say too that n is a function of x, comma y, by implication is also equal to 1 plus x squared. And that is to say n is a function of x, comma y is also a connotation of this concept. So by these indicators, we now check the partial expression. Let us partialize 2xy with respect to y. Take note that the partial differential expression is an inverse of the differential function. Differential s is partialized with respect to y, while differential y is partialized with respect to x. That is the implication of exactness, and that is the test methodology. What we are doing now is the test, exactness test. Exactness test. And in exactness test, we partialize this. If the partial derivative of 2xy, which is a function of n, is equal to partial derivative of n, which is also 1 plus x squared, once they are equal with respect to x, then it is said to be exact. Now, let us partialize it. In partial differential equation, we are only going to differentiate y, even though there is constant a and variable x. Variable x is not seen as a variable when you are differentiating partially with respect to y. It is seen as a constant. So therefore, this gives us 2x multiplied by 1. But we are differentiating y, which is 1. Is also equal to the partial derivative of 1, which is 0. Differentiate x squared, which is 2x. So at the end of the day, by implication of partial differential equation, it means that 2x is equal to 2x, which means it is equal to exact equation. Now, in this exact test, this is the test that the first order differential equation is exact, and it is ripe enough to undergo the procedure of solution mechanism of exact first order differential equation. How do you now solve the first order differential equation that is exact? We come back to ab initio, the main question itself. And this gives us the initial question which we have tested, and it is said it has undergone exactness test. What we just done is called exactness test. Exactness test. The test for exactness. And it was fruitful, it was good. It went well as an exact equation. So you now come back to 2xy differential x plus 1 plus x squared differential y is equal to 0. What we do here, we integrate m is a function of x comma y differential x plus k is a function of y. That's what you do. That's what you do. So if we now integrate it, it will now be integral of what we had here, 2xy differential x plus constant with respect to y. When we integrate with respect to s, that is partial integration, the constant of integration will be with respect to y. And that is to say, this expression will now give us 2x squared y over 2 plus arbitrary constant k function of y. And this gives us x squared y plus k is a function of y. We can call this equation 1. You can call this equation 1. We have just dealt with the m is a function of x comma y. What m is a function of x comma y simply implies that it is a partial expression that is recognizing many variables. In fact, this is connected to functions of two variables or functions of many variables. So we now go to the next part of it, which is integral function of 1 plus x squared differential y. And that is the connotation of integral. N is a function of x comma y differential y. And by implication, when this is integrated, it gives you integral of 1 differential y plus integral of s squared differential y when we open the bracket of this function. What we've just succeeded in doing is to integrate this concept. And when integrated, you have this expression. And it is broken down into y plus x squared y. If we integrate 1 dy with respect to y, what you'll be having is y. And if you integrate s squared dy, you'll be having s squared y. And this is equation 2, but take note that there will be a constant after integration, and that is k is a function of x. K is a function of x plus k is a function of x. So that is to say that at the end of the day, our equation 2 will become y plus x squared y plus k is a function of x is equation 2. We compare equation 2 and 1 and add them together without any repetition and say, therefore, C, which is the general constant, for exactness expression. In exactness, there must be, from the two solutions, equation 1 and equation 2, there must be exactly the same concept, which is s squared y, which is found in equation 1, and s squared y is also found in equation 2. You pick one, which is s squared y, and also add y. So we now repeat y plus x squared y is equal to C. It was not this that is the answer. We have to mix this and this together, but because it's repeated here, sometimes when you read on your own, you think you just chose this. No. The answer is a conglomeration of the two equations, equation 1 and equation 2. So now what we do is to expunge the constant function of y and the constant function of x and merge the two equations and equate it to constant c. This constant c, we will now have our factor as c is equal to y bracket 1 plus x squared. And finally, by subject formula relationship, y is equal to c over 1 plus x squared. This is a typical exact first order differential equation.